Okay, hello everyone. Welcome back to Advanced Plus Plus. Today we're going to be talking about regularization and optimization of deep neural network architectures. So we're going to be going over a lot of, thankfully not very complicated, but very, very useful and ubiquitously used applications, or not applications, methodologies used in applications of deep learning. And a lot of these methods that we're going to be going over today are used all over the place. If you read a paper, you're going to see like at least one of these things we discussed today, no matter what the paper is, if it's about machine learning, obviously. Okay, so let's get started. Slides are here as always, right here. So let us know if that doesn't work for whatever reason. Yeah, so there's a collab. Yeah, I mean, as you guys have seen by now, like these collabs are kind of just here for you guys to play around with. It's not like advanced track where we like do it off of a collab. Um, but it's here nonetheless. And here's the slides again, feedback form as usual, attendance code as usual, and our GitHub link as usual, which just got covered by Google Slides, but that's okay. Okay. Here's the schedule. So the astute among you may notice that we swapped around two of these. We were actually supposed to do autoencoders this week, but yeah, we had to switch it. So we're doing this one this week. And then so keep in mind there's no workshop next week. There's a holiday next week. But then week 8 and 9 we're gonna be going over autoencoders are very commonly used in the field today even, so very useful stuff. And then we have a fun workshop taught by I believe Vaishnavi and is it Vaishnavi and Arjun? You guys can correct me if I'm wrong. They're gonna go over quantum machine learning, which I honestly know nothing about, so I'll be learning along with you guys on that. So I think it'll be fun. But yeah, so let's get started on we'll start with regularization. This is probably a term maybe like a few of you have heard of before, if you're reading around in the field and stuff. But we're gonna talk about it in detail today. So let's first have a conversation about why is it good to use. So this is stuff we've discussed in the past and earlier in Advanced Plus Plus and a lot in Advanced Track. So can someone maybe unmute and say what are the benefits of using like a more complex model as opposed to just like a linear classifier or something, just at a high
express
level?
more oh express more complicated relationships better.
Okay, well that's what the slides. Okay, I guess it says that on the slide, but you wanna more detail, please?
Okay, in the case of say a linear model, if you had a graph that looked kind of logarithmic, it would be a very poor fit. But if you had say the like Taylor expansion of the logarithm, it would fit the data much better.
Yeah, so that's really good. So yeah, and that's kind of an idea at a more simple level that you'll see if you click on this graph. If you guys are on this, if you click on this link, if you're on the slides, so it's showing that there's some data that has to be modeled, and then it's showing how if you use degree 1 polynomial, it's not able to fit the data as well. But if you use a degree 2 polynomial, then it's able to fit to the data better. So in general, like cool, yay, we should use complex models. But as we all know, probably, um, this comes with its own problems because the more complex model you use, the more because it has more expressive capacity, the potential for overfitting to take place is substantially higher. So we've discussed in the past. So the idea of overfitting is that, as the name suggests, because we're training on one specific subset of some larger data set, right, which we denote our training set, because we're only training on that, all the model usually cares about so far when we've been talking about our loss functions and how we're optimizing stuff is just getting that loss value of the kind of relative distance between our expected result and our actual result to be as low as possible, right? So as we discussed last week in the Fair ML workshop, um, um, machine learning models just based on this construct are kind of not so smart in some ways because all they care about is minimizing that loss value. And it's going to do exactly what the constraints of our loss are telling it to do. So if we're just trying to minimize the distance between the expected result and the actual result in our training set, then our model is just going to try to basically, after a while, all it's going to try to do is memorize the training set, right? This is all stuff hopefully we were somewhat familiar with, right? So it's just going to try to memorize the training set, and it's going to be able to do that more effectively if you use a more complex model, right? So if you have a linear model, right, there's no way that you can overfit the data usually, right? Because there's not that much expressive capacity. It has to just be a line, right? But if I'm using some very complex function, then I have a lot more potential to make a lot more of an intricate fit along this boundary here, right? But this boundary that we're looking at on the screen right now is only reflective of the test data, right? Or the training data, right? So it, it's very likely that our test data is more along, this kind of boundary here that we see in the appropriate fitting example, where, yeah, sure, we'll miss a few examples at the training time, as you guys can see here, like these two X's are in the wrong spot, are on the wrong side of the decision boundary. But hopefully we can all agree that this is a more generalizable fit to the data than this model here. This one's fitting too much to the training set and is not necessarily reflective of the actual data distribution at large. So is there any basic questions about like what overfitting is? Okay, cool. Hopefully we're all somewhat familiar with that. So the idea of regularization is we want to still be able to use complex models, but we want to kind of give it a nudge in the correct direction and place some additional constraints such that overfitting will happen less. So we still have a lot of expressive capacity, which is a lot of times very useful for learning complex relationships, but we want to kind of tone it back a little bit. Use some methods to make sure it doesn't overfit too much, like we're seeing on the right here. Okay. So one general definition that if you guys read the deep learning textbook by Ian Goodfellow, one definition they provide of regularization is any measure taken to increase the testing / validation performance of your model, but not necessarily improve the training performance, right? And this makes sense, right? Because if we're seeing here, if we're having an appropriate fit, we're actually doing worse on our training set here, right? Like the middle example here actually does worse on this training set than our overfit example does, right? Because it misses these 2 points, but the overfit example gets all of them right. So we're actually doing worse, right, on the training set when we're looking at our appropriate fit example. But we're going to see that this is a more generalizable and more appropriate model. And very, very likely this is going to perform a lot better on the test data, which is really what we care about, right? We don't really care in essence how well it does on the training data. Like we like it when it does well on the training data because that should hopefully mean it does decent on the test data. But if you're doing great on the training data and horrible on the test data, your model is really just useless, right? You can't deploy your model to any generalizable use case. So it's very important that we focus doing well on the test data. Okay. So yeah, so this is kind of just stuff that I just discussed, right? So this is like an example of overfitting on the right. I'm sure you guys have all seen like a graph like this before, like a basic like outline like this before, where we see like a lot of the times what you'll observe is your training loss is going to keep going down, down. Same with your accuracy. Your accuracy is going to keep going up and up as you train over more epochs. But after a certain point, we see it starts doing worse on the test data, because at this kind of line right here, this is when the model kind of transitions. I don't think transition is the right word, but it kind of is fitting too much to the training data, and it's becoming to the point where it's just memorizing stuff. And if you're just memorizing this, then of course you're going to do really bad on this other test set, right? So there's a fine line that we need to meet here. And so before we go into talking about some regularization methods, what are some methods maybe you guys can think of that would improve the test time performance of the model, but not necessarily improve the training time performance? There's some very like basic examples that maybe you guys have on the top of your heads.
I guess we can try and penalize the weights. Like just make sure they aren't too big, I think.
Yeah. So yeah, that's a very common way that we carry out regularization. So we're going to go over that in the next few slides. So the most common ways that we do that are referred to as L1 and L2 regularizations. And we'll see the benefits and drawbacks of each of those methods. They're very similar in a lot of ways. But yeah, the idea is you prevent the weights from getting too large. And we'll see why that helps the model generalize in a few slides. But that's one good method. A very simple method that you could use is something called early stopping, right? And this could be something that we think of just by looking at this graph, right? So obviously, if we want the test time, if we want the training, the test accuracy to be as high as possible, so we want optimally our test loss to be as low as possible, right? We should optimally want to stop right here, right? You guys see this line? We should stop training right here, because if we train more, our test loss actually goes up. So we start doing worse after here, right? Like we said, we don't actually care about the training performance, right? We care more about the test performance. So if we stopped training right here at the minimum of this kind of loss curve, then our model would have optimal performance, right? But it would actually perform worse on the training set, right? So once again, this aligns with the definition that we proposed of regularization. Of we don't necessarily care if the training performance gets better. A lot of times it'll actually be worse, but hopefully we're improving our test performance. So there's a lot of very simple things that you can do to help with this. So yeah, let's go over um, the most canonical, I guess, example of regularization, L1 and L2 regularization. So um, as you said, Hamlin, so the idea is that we want to penalize the weights from being too large, okay? So this is an additional constraint that we add to our loss function, okay? So if our loss function can be any loss function that you guys have seen before, any loss function we've discussed in the past, stuff like mean squared error, cross entropy loss, whatever your loss function was originally, right? We have some loss function. No matter what it is, let's add this additional term to it. Okay. And what this additional term is going to slightly vary based on whether we're using L1 or L2 regularization, but we'll explore that in a second. But the idea is you add this additional term, which is going to increase the loss the larger the weights are, right? Hopefully you guys can see this, right? So the higher our weights are, right, the higher our losses, right? Hopefully that's clear. And the objective that the neural network cares about, or our model in general cares about, is getting this loss value as low as possible, right? So if we're penalizing the model, if we're increasing the loss of the model when it has large weights, it's going to want to reduce its weights, right? It's going to reduce the magnitudes of its weights to be smaller values, right? So if we're reducing the magnitude of our weights to be smaller values, then that's also going to decrease our loss, right? But it's not just doing this, right? It's not just decreasing the weights as small as possible, because if that's all we were doing, then the model would just converge to having zero weights for everything, right? And that would suck. But what we do is we add it to what our loss already was, right? So this loss value, this error value, is supposed to give some sort of metric, as we've discussed in the past, of how well the model is actually performing on the data. How accurate is it being, right? So we're kind of combining these two things. So the model has to look at two things now, right? It has to look at, am I being accurate on the training samples? And am I also keeping my weights in check? So it has to care about both of these things if it really cares about getting its loss down, which it does. So it'll care about both of these things. Now, there's an additional hyperparameter that we have to introduce here, right? It's this little lambda term right here. So can someone maybe discuss what you guys think may happen if this lambda value is very large, and then something that might happen if the lambda value is very small?
Well, if lambda is too small, then it's like you're not doing regularization at all. Versus if lambda is too large, then the neural network will prioritize bringing all the weights as low as possible instead of getting an accurate result.
Yep, perfect answer. So yeah, that's exactly right. So if this lambda term is zero, right, then we literally just don't, this just goes away, right? And then it just becomes what we had before. So the closer our lambda term is to zero, the closer we're getting to just not regularizing, right? So the higher our lambda term here is, the basically the stronger or the more aggressively we're regularizing our model. And then we don't want to make it too high, because if we make this value super, super large, then the model is going to be like, wait, I don't care about this term, this error term on the left anymore. I'm just going to focus on this, because if I just focus on this, my loss will get really, really low, because this has a very small impact on my loss since this lambda term is very large. Right? As we discussed last week in the more in the more specified case when we were talking about bias and fairness in ML, the model is just going to do whatever it can to minimize this loss function, right? So if it sees that it can only focus, if it just has to focus on this to minimize the loss, then it's just going to focus on this, right? Okay, so now that we have the high level idea, let's talk about the maybe differences between L1 and L2 regularization. Okay, so L1 regularization, so the terms L1 and L2 come from the norm that we're using to calculate the magnitudes of the weights, right? So we're using the L1 norm here, right? To calculate the values for or calculate the magnitudes of the weights here. And that's going to have certain effects on our models, versus here we're using the L2 norm, so the Euclidean norm instead, right? So this is going to have some impacts on the way our models learn, and the distribution of the weights. So most notably, the most notable difference between L1 and L2 regularization is that you're going to see sparser weights in the L1 regularization example. So you're going to see that a lot of your weights are just going to go to 0. And then, so a lot of your weights are going to be kind of saturated towards larger values, and then a lot of your weights are going to be just converging very close to 0. So does anyone have an idea why, if we use L1 regularization, maybe why would some of our weights maybe go a lot closer to 0? Why would it be kind of more sparse or more all or nothing than if we use this L2 regularization?
With L2, like it only like significantly punishes the network if it has like obscenely large weights, versus with L1 it's on like a linear scale, so it's not as like robust, I guess.
You okay? Yeah, that's in the correct direction. Yeah. So kind of one way. There's a lot of ways you can think about why this is the case. There's a lot of intuition behind why this may be the case. So yeah, like you said, like one case is that just the way that this is calculated, right? It's going to be a much smoother curve, and you're going to have a lot more significant penalties, right? When you're at very large weight values, and then you're going to do a large penalty, right? But think about what happens when our weights are below, like the magnitude of the weight is below the value 1, right? For any specific weight in our network. Then when we square it, that value is going to get even smaller than it was before, right? If you square a value less than 1, right, that number is going to go down. If you square a number that's above 1, that value is going to go up, right? So if our weights are already kind of close-ish to 0, there's not going to be a very large penalty here, right? Because when you multiply it, when you square it, that value is going to get even smaller, right? So then the penalty that's incurred here is going to be quite small if you're squaring it. But if we don't square it, then it's not getting any smaller, right? Like 0.5 times 0.5, right, is 0.25, versus just 0.5 on its own is just 0.5. So the penalty here is going to be larger when we have weights that are close to 0, as opposed to our L2 regularization example. So that's why a lot of times you'll observe that the L1 regularization it's like I've been saying, we refer to that as a more sparse model. So a lot of the weights are closer to 0.
Paymon, can you just add something?
Yeah, of course.
So one more reason why L1 weights tend to go to 0 is that if you take the derivative of the loss with respect to the weights, right, ignoring the first error term, the derivative of Wi would just be +1 or -1 depending on the sign. So independent of how big or small Wi is, the magnitude of the gradient is always just like 1. So there's always pressure on Wi to become smaller and smaller. But when you have the L2 norm and you have Wi square, the derivative is 2 into Wi. So that's dependent on the magnitude of Wi itself. So when Wi square is very big, 2 into Wi is also pretty big. And so there'll be a correction towards a smaller number. And when Wi square is incredibly small, 2 into Wi is also pretty small. and so the corrective pressure is also reduced. So I guess like that's also a reason why the L2 norm has a smoother function, while there's a risk with L1 norms of like the weights just going to 0.
Yeah, that's exactly correct. And hopefully maybe you guys can see that there's a reason the what Varun said and what I said in our sense are very intimately related with each other, right? The reason why these two things happen, it would make intuitive sense that if we're just looking at the value of the loss, that we're going to incur less of a penalty the closer we are to 0 and we're squaring it. And then when we take the derivative, we also see when we do the update, we're going to incur less of a penalty because it's 2 times W, like Varun said. So if the W value is very small, we're incurring less of a penalty and less of a drastic updates to our weight parameters. And these two things are intimately related. So yeah, thank you for adding that, Varun. So we spent a lot of time on that slide. So I think Varun's going to do this slide. So you can just unmute, Varun. I'll keep sharing. I'll just mute my mic for a sec.
Yeah. So I just wanted to provide some motivation for why we want to penalize large weights in the first place, right? Because when initially when I came across regularization, I was like, I can't see immediately why larger weights are worse than smaller weights. And when I looked into it, this is what I found. So if you look at this picture, right, once again, the underfitting, just right, and overfitting, you'll see that in the overfitting case, uh, even if your input X varies by a tiny amount, your output Y can vary wildly. So that's the motivation behind what an overfitting function looks like. Even if your input varies by just a little bit, your output can fluctuate widely. So to reduce this impact, we try to look at the following objective. So if you look at this equation over here, intuitively what it's saying is that suppose I have two inputs X and Y. Like, I guess the notation is a little confusing. You can think of this as X1 and X2, right? So if you have 2 points X1 and X2, and then you look at f of X1 and f of X2, their difference is at most L into the difference of the inputs, right? And like if you have some kind of objective like that and L is very small, it means that if X and Y, if X and X1 and X2 are relatively close together, so is f of X1 and f of X2. And that's what you have in this just right graph, where if X1 and X2 vary just a little bit, f of X1 and f of X2 won't vary by too much. And so ideally, you want to make this L for your neural network as small as possible. And it turns out that this constant L is dependent on the weights. So if you have weights with very large norms, then L tends to be very big as well. And if you have weights with smaller norms, then L also tends to be smaller. So since a smaller norm is going to give you a function that fluctuates less, that's why you want to make sure that your weight norms are not too big. So that's the motivation behind why we try something like L2 and L1 regularization in the first place.
Yeah, that's a great point. Yeah, I was also like, I remember when I was first learning this stuff, and I was like, why do we care if the weights are small, right? And even more intuitive way to just think about that, right, is if your weights are very large, right, then, and remember the way we feed forward through the network is we first take our input, then we multiply it by some weight matrix, right, for our first hidden layer of neurons. We get the first hidden layer activations. We keep doing that forward and forward and forward and forward until we get to the output, right, until we get to our scores. So if your weights throughout that process are very large, they're gonna have a lot of variance, right? The variance between your weight values is, if they're larger on balance, your weight values are gonna vary more. And then they're also, just because they're larger, if you change X a little bit, then you're gonna end up with a very different score than if you had a regularized set of weights where your weights are very small. If your weights are all very small, then if you change X a little bit and then you pass through the network and get your scores, you're gonna get closer to the same scores, since there's not as much variance between the values of the weights, since they're all closer together and they're all closer towards 0 than they would be otherwise. So yeah, there's a lot of reasons why L1 and L2 regularization are good. Okay, so okay, I think yeah, so this slide's just talking about the hyperparameter, I guess. yeah, I think this is just formalizing stuff that we already talked about and stuff we already understand, hopefully. So yeah, remember lambda is just a single additional hyperparameter that we have to select. This can be tuned just like any other hyperparameter using any of the methods we've talked about in the past. You can use n-fold cross validation. You can just do a search over different hyperparameters. There's a lot of different ways you can choose that, just like any hyperparameter. Once again, we have some intuitions of like what good regularization values are. Like usually something around like 0.1, I don't know, in that ballpark. It very much depends on the model you're training, the architecture of your model, but that's just some intuition to go off of. So yeah. Yeah, okay, okay, these slides are just stuff we've already been over, so I'm just gonna skip this. Okay, so let's do an example so we can kind of see, okay, this isn't really an example. This is just like more math so you guys can see the gradients better and actually see the update rules. So let's say we're doing a linear regression problem and then we're just using, you know, basic gradient descent to update our weights, right? As we've also hopefully seen in an advanced track or we've seen before, we're just gonna update our weights towards the direction of the negative gradient times this little learning rate parameter, right? So we're just going to use basic gradient descent here. So let's see what happens. Let's see how our loss value changes now that we have this additional term here, right? So Varun mentioned this earlier, right? So when we have L1 regularization, what's going to happen is that this derivative is always going to be, yeah, like Varun said, it's going to be like 1 times whatever this parameter is, right? So here it's just going to come out to a lambda, and if your W is negative lambda, right? But the observed difference that we see here is that when we have L2 regularization, right? Now this term is, like Varun said, is a function of the weights, right? So now hopefully this is more clear that if this is our update rule, right? In L1 regularization, it doesn't matter. Like if your weights were really big or really close to 0, you're still going to just penalize it by a constant factor. Okay. Whereas in L2 regularization, we're going to penalize it by this factor, some constant factor times the weight. So once again, if the weights are very small, this value is going to be very small. And it's not going to have a very significant impact on the way we update our weights. So this leads to a smoother loss curve as a result. And generally, that's what you want when you're training networks. So you're going to see L2 regularization used a lot more than L1 regularization. There are certain contexts for more specialized tasks where it makes more sense to use L1 regularization, but I'm not going to go over those right now. Okay. Yeah. So we have already discussed all of this. I'm going to skip this. Okay. Now something new. So, okay, we might need to rework these slides a little bit because we had like way too many slides for regularization, and then we only have like 1 slide for this. And I think this is like really important. So, okay, dropout. So dropout is a very commonly used method of performing regularization on what would otherwise be like fully connected networks. So just like our basic networks that we looked at the beginning of advanced track, where we just have a bunch of rows of neurons of hidden layers, and then we want to train a model on it, right? So we can do something called dropout, which is a very effective form of regularization, one of the most effective forms of regularization, and one that you'll see very commonly applied to feed forward linear feed forward layers in state-of-the-art neural networks. Okay, so what's the idea? So we're gonna introduce another hyperparameter. We're gonna call it P. Okay, and this hyperparameter P represents the probability at each hidden layer that we drop any neuron in the hidden layer. Okay, so let me explain that more concretely, right? So let's use this visual here. So in our network here, we have a 3-layer network, right? So we have the input layer, then our 3 layers. So we have 5 neurons in this first hidden layer, 5 neurons in the second hidden layer, and then we have our output here, right? So if our p-value is 0.5, okay, that means when we go through and look at this first hidden layer, we're going to kind of remove a neuron, kind of exit out of the equation, just forget about it, with a 0.5 probability. So 50% chance that we drop a neuron in any given hidden layer, okay? And then what happens is that you get a network that looks like this, okay? So then you have, so we turned off some of these neurons here, right? So this is just randomly selected. You turned off some of the neurons, And then now basically what turning off the neurons means is that you basically set the weights that brings you to this neuron to 0, right? So that just kind of cuts off the connection to that neuron. And then you do this for every layer, right? And then you do this for every single time you feed forward through the network, okay? So every batch of examples you feed forward, every training example you feed forward, you do this again, right? So you don't just do this once at the beginning and then just call it good, right? Because then you're not actually doing anything. Now you still have the same model. You still only have one model, right? The benefit of using dropout is now we're effectively training our on our task over a bunch of different models, right? If you think about it, we're training over a bunch of different models now, because maybe the first time when you feed forward the first training example, you drop this first neuron, this third neuron, and this fourth neuron, right? And that has one feed forward pass, right? That's one way that the network was fed forward. Now you pass through a different example, right? So example 2. And then when you're feeding forward to get the score for that second example, maybe you drop like the second neuron and the fifth neuron, and then you keep these other 3, right? So it's completely random. The only thing you're choosing is the probability that you drop a certain neuron. So intuitively, the reason why this is really good is there's this more general concept that I think we should actually like have separate slides to introduce before we talk about this, because it helps with understanding this. But there's another concept that's very popular in terms of regularization called ensemble learning, right? And the idea of ensemble learning is that I'm going to train a bunch of different neural networks all to do the same task, okay? And then after I train all of those networks, every time I want to predict something, I'm going to feed forward through all of those neural networks, get the result of all of them, and then get either the average result or the majority result, right? So imagine you're training on the MNIST data set, right? The handwritten digit data set. And you have to identify a handwritten digit being 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So let's say I train 10 models that all of their jobs are just to do MNIST, right? To classify MNIST. And then let's say we feed it an image where the output is supposed to be 1, right? So it's a hand-drawn digit of a 1, and the network has to predict this correctly. Okay, so if we have 10 models, right? Let's say 7 of them say that the digit is a 1, but 3 of them say it's like a 4, right? But it's 4 is not correct, right? So 3 of them got the wrong answer, but 7 of them still got the correct answer, right? So if we're taking the majority vote of those 10 classifiers, we'll get the correct we'll get the correct result. But if we only trained one network, right, it was possible that that one network could have been one of the ones that got it wrong, right? So then in this sense, if you train a bunch of different models, right, your results become more robust, right? Because if you want to predict something wrong, then all of your networks, right, or at least a majority of your networks are going to have to get the answer wrong, right? That's the only way that you're going to get it wrong. So it's going to be harder for you to get the answer wrong if you train more models. Now, this brings us back to dropout, right? So as I discussed earlier, in dropout, what we're effectively doing is every time you pass forward an example, you're using a sort of different network, right? Because the weights that are activated in the network are different. So it's effectively, you're using a different neural network every single time. So this is exactly like ensemble learning, where you just train a bunch of different models all at once, and then you just average the results. It has the same effect of doing that, but it's really smart. Because why is this a lot smarter than just using ensemble learning? Does anyone have an idea in terms of the time complexity and how hard it is to do this stuff? Why is this a lot smarter than training 10 different models?
You're training just one, no?
Yeah, exactly, right? So although it gives you the perception that you're kind of training on a different model every single time because you have different weights activated, the kind of skeletal structure of your model is exactly the same. You don't actually train 10 models. You just have one model, and you can perform this little trick that we talked about where you randomly drop some of the weights from your feeding forward every single time. And then effectively you're training on a bunch of different networks, but you're only really training once, right? So you save a lot of time, and it has a lot of computation. It adds a lot of robustness to your model for intuitively the same reason as our ensemble learning example, where if we would have to get a lot of our models getting the answer wrong instead of just one model getting our answer wrong. So I don't know, Varun or Justin, there's a lot to unpack here. So if you guys want to add anything, feel free.
Yeah, actually, so what Paymon said is definitely a better way to think about it. Like think about it in terms of ensemble learning. But I felt that one more intuitive way you could look at this is if you think of every like neuron in your neural network as learning some sort of pattern in your data. Suppose by chance that like one or two neurons are just responsible for memorizing a couple of training data samples, right? The idea is that even if you kick those two neurons out of your neural network, you want the rest of your neurons to have learned the actual patterns in the data. So just because a couple of them have memorized the training data does not mean that the neural network should be performing badly. So the idea is that if you just zero out some neurons here and there, there's a lower risk of your neural network essentially memorizing the training data and actually learning the patterns that it needs to.
Yeah, like you're keeping it on its toes, right? Because every single time you're gonna change the the weights it has to work with, the neurons it has to work with. So it can't really get comfortable and just sit down and just memorize stuff, right? Because you're keeping it on its toes. You're changing the weights it has every single time. So it has to really like learn generalizable features if it's gonna do well. Because if you're changing it up every single time and it's just trying to memorize something, every single time it starts just settling its weights down to memorize some training set, it's gonna screw up again because next time you're gonna switch it again, and then all the neurons that it used to just memorize the training example, it's not gonna work because you turned some of them off. So then it has to become really robust and learn really more abstract features of the data if it's gonna be successful, even if you drop random weights every time. So yeah, in practice, right? Hopefully you guys can see this is really easy to implement. All you really have to do is, yeah, you just like when you're feeding forward, just like survey a random sample, um, like a mask, we'll call it, of ones and zeros, right? And then you just, and it'll be the same like size as whatever your hidden layer is, right? And just randomly make 60% of them ones, and then 40% of them zeros if p is 0.6, right? Then then you just apply that mask against the weights of your networks. You'll just directly element wise multiply it, and then it'll just like set a bunch of those weights to zero, right? Randomly based on the values that your mask incurred. Okay. So hopefully that's clear. As always, like just ask any questions if you do. Okay, cool. So those are some basic regularization methods. Now we're going to talk about optimization, right? So optimization refers to the algorithm we use to actually update the weights. It has nothing to do with how the gradient itself is calculated. It has to do with how we use those gradients to update the weights, right? So the way we're all familiar with, hopefully the methodology that we're all familiar with is that of gradient descent or stochastic gradient descent, right? And the idea is you'll just take an update type of whatever the gradient in the negative direction is, right? And then multiply that by your learning rate, right? So the equation, right? Like this equation that hopefully we've all seen, right? You're just updating straight in the direction of the negative gradient times your learning rate every time, right? So this is very simple, and a lot of times it can do like sort of get the job done, right? But there's a lot that we can do to improve this. A lot more clever methods that we can use to update our weights, even given the same set of gradients, right? We can use them in a more smart manner. So is this where you take it, Varun, or do I have a few more slides?
Yeah, I can go ahead from here.
Okay, cool. So I'm gonna stop sharing then, and then Varun can share his screen.
Yeah,
So let me stop share.
cool. Okay. So yeah, like Paymon mentioned, now we're going into algorithms to actually implement some of these methods and various different optimization techniques. So we already looked at some motivation for why we want to modify gradient descent, and that's because, like, let's say you have your data set, right? Let's say it's not just 100 data points, but it's more like 1,000,000. Um, if you remember, in at least in linear regression, if you look at the gradient, you have a large you have terms like X transpose X and so on with large matrix multiplications. And those can take a lot of time. And note that like while you're doing so many large computations, you aren't even updating the weights a couple of times, right? It's just a single update that requires such a large amount of computation, which is why if you process the entire data set before every update, you converge to your optimal weights really slowly, right? Because every time you want to make an update, you have to look at a million data points. A better idea might be that instead of looking at a million data points, we look at every individual data point. So we look at data point 1, it tells us, okay, the loss is a little high for this data point, so let's adjust the weights a little bit. And then let's go to data point 2, and so on. So instead, you make an update after every single data point so that your weights keep getting nudged in the right direction and doesn't take, you don't have to look at a million data points before making a single update. Now, once again, this has its own problems, right? If you look at every single data point, there's going to be a lot of fluctuation. If two data points differ significantly, you might end up in a situation where the first data point makes all the gradients increase by like +5, and the second one makes them all decrease by 5, and then you never get anywhere. Your algorithm just doesn't converge, right? That's what it means by high variance in training samples. So if each individual data point varies too much, your gradient descent is going to look very noisy. And so both these have their own sorts of problems. So the best idea is to combine the merits of both of them. So instead of looking at the entire data set, instead of looking at like 1 million data points, maybe it's better to look at just 1,000 or 100 data points. Now, this is large enough so that you don't have the sort of crazy variance in your gradient descent, and it's not super noisy. But at the same time, it's not as large as 1 million, so you can make updates to your weights a lot more frequently. So that's basically what mini batch gradient descent is. You split your training set into mini batches, and what size that should be is dependent on a lot of different factors. It depends on what model architecture you're using, what the size of your overall data set is, and so on. So it can be, so that depends on, that's an implementation choice. But the essential idea is that you first look at the first 100 examples in your training set, update the weights, and then go to the next 100 examples, and so on. Once you run through all 1 million, so if you have like 1,000 examples, and each batch is, let's say, 100 examples, then you'd have 10 mini batches. And once you update all the weights for all 10 mini batches, that entire step is called a single epoch. So of course, you can also have multiple epochs, and that's what you need. So you keep going through the batches again and again, but this just has the added advantage that you make updates to your weights a lot faster, and so you tend to converge a lot faster as well. Yeah, so does anyone have any questions about mini batch gradient descent so far? Any questions about stochastic gradient descent, why we don't like using the entire data set, and so on?
If time and memory were not an issue, would the first option, I forget what it was called, was it just gradient descent? Would that be the best option for accuracy? Normal gradient descent, okay.
Yeah, so do you want me to answer this, Varun?
Oh, yeah, sure.
Okay, so yeah, so if you update, so think about what the gradient is and what we're taking the gradient with respect to, right? The loss function is a function of your training inputs and the weights in your network. So if you want to truly calculate the best direction to step to decrease the loss as fast as possible, right? You would ideally need to calculate the gradient with respect to all of the parameters in the network, that which are all of the parameters by which your loss is defined. And if you want to do that, because your loss is technically defined over all of your training examples, then yes, you'd have to take the gradient with respect to all of your training examples, and that would get you the most accurate direction to step in. So that's correct. To answer your question, yes. Like if you want the most accurate direction to step in, technically it makes sense to update over all of the examples. Now, like Varun said, this isn't a good idea because it takes a lot more time. And in practice, right, that if you get a decent approximation of the correct direction to step in by using less examples, then on average, you're going to step in the correct direction. Hopefully that intuitively makes sense. That if you're making good approximations where the average guess is where the correct guess should be, then if on average your guess is correct, even if one single guess and one single update step might take you a little bit in the wrong direction, over time, if you keep doing this, eventually you'll get in the correct direction and then you'll converge and you'll do it a lot faster. So yeah.
Yeah, but to answer the question directly, yeah, I think if you use the entire data set, it's not practical, but theoretically, it's probably going to give you the best result. On the other hand, in a more realistic situation, I don't know, this is just me making some guesses, but suppose you're like a big tech company and you have data that's constantly coming in batches. Note that when you're making these gradient descent updates for each batch, your last update is probably going to fit your newest batch closely. So if you keep getting newer batches of data, maybe you want to start fitting those better. So there's also like if you want to fit new data better, it might be better to use batch gradient, mini batch gradient descent. But once again, that's just my guess. I might be wrong.
No, I think that makes sense. So I think what Varun's saying is like if over time like the distribution of your data is changing, right? Like the data, like we discussed last week, data comes from the world. The world is always changing. And if you're dynamically trying to update your model to deal with what's happening here and now today, right? You want it to care more about the data that's coming in today, right? Not all the data of all time, not the data from 200 years ago, right? Because that might not be reflective of what you actually want to be doing anymore. So that's actually really, I actually hadn't thought about that. That's another great example of in practice why mini batch gradient descent is good. Yeah.
Yeah. So uh, let's go ahead and see some other ways of improving gradient descent. So this is just the standard gradient descent update rule. You have your weights theta t plus 1, which is basically theta t plus minus the learning rate into the gradient. So we're essentially, now we're just going to play around with this equation and see if we can come up with any methods that's going to improve this update rule. That's broadly what all the optimizers were doing today. Like that's essentially it. Just modification of the update rules that we would expect to get better results. So, okay, what are the problems with gradient descent? Number one, learning rate. Finding a good learning rate can be difficult. And in fact, a lot of research goes into finding a good learning rate. Right? Because if you're too big, you might your gradients might be wildly large. You might fluctuate from one solution to the other, and so on. Too small, and you're just not doing anything. Right? You're hardly moving from where you're already at. So that basically means that you have an optimization problem. You don't know what your optimal learning rate should be. But the problem with that is typically if you have larger learning rates, you're also able to learn a lot faster because you can move to a good solution a lot quicker. But once again, you're constrained by the fact that a large learning rate might cause you to reach a terrible solution. So that's one. So these are the kind of problems that come up in gradient descent in practice. Right, and these are some of the other problems. If you look at the weights in your first layer and your weights in maybe your 50th layer, they might require very different learning rates. And it's very hard for us as like machine learning engineers or researchers to just say that, okay, the 50th layer has to have this particular learning rate at iteration number 7042, right? You simply have no way of doing that. So we should try to look at optimizers that automate this for us. And once again, you have the problem of gradient descent getting caught in local minima. This could once again be related to having a very small learning rate, so you're not escaping the local minima. But these are broadly the issues. I'm not sure if we'll be able to address every single one of these problems in this workshop because honestly, this is a lot of content and a lot of research goes into these problems individually, but we'll try to do the best that we can. So number one is something called momentum. And this addresses a problem that we brought up before, which is most pronounced in stochastic gradient descent, right? Where if you look, stochastic gradient descent is essentially making an update for every single data point. And in that case, it can get quite noisy, right? Your gradient can vary wildly, and so you can have some sort of fluctuation like this until you reach the minimum. And that's obviously not ideal because you want to take a path straight to your optimal solution and not just wander around in between. And so the way you can counteract this is by saying that, okay, on average, I'm going in the right direction. So I know that this new data point is telling me that I need to go in this direction, but let me combine that with my prior knowledge of what gradients have been in the last 10 updates. So what momentum essentially is that, let's say my prior updates have been in broadly one particular direction. With the new data point, I just use that to change the direction slightly. Intuitively, you can think of this as gradually changing your steering wheel as opposed to making a really sharp turn. So that's the intuition behind why you would use something like momentum. And this is the mathematical formulation of how you would go ahead and implement this. So note that normally you would just do the second rule, right? Theta t plus 1 is equal to your weights at time t minus the learning rate into your gradient. But you replace the gradient with this term called v, where v is sort of like a momentum vector. And what it essentially does is it says, okay, instead of using the gradient, I'm going to use, let's say, beta into vt minus 1. So this could be something like 0.99 or 0.9, I think, in practice, plus 1 minus beta into the gradient of my current batch or my current data point. So intuitively, what this means is that vt minus 1 is in some sense the average of your past gradients, and 1 minus beta into your current gradient, the gradient of your current batch, is the modification you're making to the existing gradient. And so now when you make this update, it's more nuanced, it's a smoother turn, and you're not going to have like wildly fluctuating gradients anymore. Like in this picture, you might still have some fluctuations, but you're going to try to minimize that as much as possible. Yeah. Thanks, Zahir. Yeah. So that's the idea of why you would want something like momentum. Basically, extract the benefits of something like mini batch gradient descent, but at the same time, not allow your gradient to fluctuate wildly. And yeah, you can think of this essentially as just a ball rolling down a hill. It's going to change directions every now and then as it approaches the bottom. But if it's going at a certain speed, it's going to continue in the direction for a little bit before changing direction again. Yeah, I guess we've covered all of this. Yeah, and typically in practice, beta is set to 0.9, which personally, in my opinion, I thought that was really high, but empirically, that's what seems to work best. And I guess the important thing to note is that VT itself keeps changing. So my current gradient at this point becomes part of the momentum for my future updates. Yeah.
Yeah, so let's ask, what are kind of the effects? So I think this is a good exercise like we did with regularization. What would be the effect of having a very small b value or beta value, and what would be the effect of having a very large beta value? So by small, we mean very close to 0, and by large, we mean very close to 1. So what would happen if it's very close to 0, and what would happen if it's very close to 1?
I guess if it's really close to 0, wouldn't you just have the regular gradient descent? Like, it seems like the momentum doesn't even affect it. And then I guess if you have a really big beta value, you're just using the previous momentum rather than updating it with the gradient.
Yeah, so yep, like all our hyperparameters, it's a question of balance, right? So we want to be able to kind of It's like I like the steering wheel example that Varun gave, right? If our B value is very close to 0, that means our steering wheel can only make very large turns, very aggressive turns, right? Because when it basically, to complete the analogy, when we have a very small beta value, right? Then basically you're just doing normal gradient descent, which means the direction you move is almost entirely determined by what the gradient was at your current time step, right? And then as you increase the B value, then the significance of the gradient at your current time step gradually becomes less and less and less and less, right? So you don't want it to be, you don't want that significance to be too low, right? Because if you figure out, oh, I need to like make I need to change my direction a little bit if I'm going to actually get to this minimum, and you're not letting it change its direction, then it's going to take a long time and it's going to kind of get stuck and it's not going to go the correct way. But if you balance it out correctly, then it's saying, okay, I see, I got to go this way. Okay, we can start moving in that direction at a respectable pace. And then if that's really the direction that we need to go in, right, then the update after this one and the one after this one and so on and so forth are going to keep telling you, oh, we should keep going in this direction. And then you'll keep turning a little more towards that direction every time, instead of just being like, oh, we should go this way and then just immediately turn in that direction, right? So that's kind of the idea behind momentum. It cares about the history of your gradients.
Yeah. So guess let's go ahead and look at the Nesterov accelerated gradient. Super fancy sounding. The idea is sort of similar, but once again, you have a similar momentum term. So this is once again beta into your history plus 1 minus beta into your gradient, except what you do is that instead of looking at the gradient at your current point, you perform the update first. So you just look at theta minus like beta into vt minus 1. So you're kind of changing your theta a little bit, computing the gradient, and then finally making your update to get theta t plus 1. And the reason you would do something like this is because you know that you should be approximately going in this direction. Like, you know that theta should eventually be going in this direction. So you're basically making a guess about what the actual gradient should be. And you're also taking advantage of the momentum. So it is a little trickier to understand, but intuitively what this means is that instead of just computing the gradient at my current point, I just take a guess. I just make a guess about what the gradient is going to be after my update and use that in my current update itself. And the effect of this is, you might be wondering, like, why can't we just update it twice? That would just be a lot simpler. And it turns out that if you do something like this, it just makes your implementation faster, and you also converge to a solution faster. That's essentially what accelerated gradient is, and it's used, and this also has the advantages of regular momentum as well. Yeah, and yeah, it's called foreknowledge. You just anticipate what the gradient is going to be, and it can make a more informed update.
Yeah, so let's look at maybe the differences between normal momentum and our Nesterov momentum and C. So if we go back to the previous slide, we can see that the only difference is what this kind of what the gradient is itself, right? So in our normal momentum, it's just like it was in stochastic gradient descent, where we just take our gradient with respect to our current weights, right? Now, if we go back to Nesterov, the only difference is what we're taking the gradient in respect to. Everything else is exactly the same. So it does exactly what we just discussed with momentum, except it's doing it we're kind of doing it preemptively. That's the way I like to think about it. You're kind of looking forward. That's why on the slides we say it's like foreknowledge. Yeah. So we kind of look forward, right? At where we look forward into the future, right? We make a prediction about the future and then make our update based on where we anticipate the gradient's going to be later on, right? So you can imagine why this would be better, right? Because if we make a guess about where it's going to be later and then make our update based on that, then on average, our guesses are going to be pretty good, right? These are not just random guesses. They're informed guesses based on the direction we have been going in the past, right? Because VT gives us an idea. VT minus 1 gives us a direction of where we've been going. So we look at where we've been going and we're saying, okay, we're probably going to keep going in this general direction. So let's preempt our calculation and calculate our gradient, assuming that we're over there now at our future time step. So then obviously just intuitively, right? If we're predicting where we're going to be and we're making our updates earlier as a result, we're going to have a faster conversions as a result. And empirically, we can see this. And there's a nice link that I don't want to show you guys yet, but we'll show it. Are we good? Actually, we can do it now because I think these are like the two um, algorithms we were going to go over. We were also going to go over Atom. Do you want to go over Atom, Varun, or no? I don't know.
I think in the interest of time,
Yeah, we can you can talk to us about Atom later. Atom is like the state of the art, and it is just it's uses all these ideas and a little bit more. But we don't have time to talk about that. But there's this nice link before we go on to batch norm. Or I guess it's yeah. So I just sent it in the chat for you guys. This gives a really nice visual, especially the second kind of animation. If you guys want to click on it, it shows like um how these different models or these different optimization techniques converge to a local minimum. So on the second image, um yeah, I think Varun's just opening it. So yeah, can you scroll down to the second one, Varun? Yeah, so you can see here. Okay, so there you guys see there's like a lot of lines here. So we've talked about SGD, so that's stochastic gradient descent. Momentum is just vanilla momentum, and then NAG is Nesterov accelerated gradient. So we've talked about those three. There's also AdaGrad, AdaDelta, RMS prop. So those three we haven't gone over yet. They use some methods to dynamically update the learning rate, which is something that Atom also does, but we're not going to talk about that. But if we look, wait, can you go back to the second one? Like the one, yeah, that one. So just look at the red, green, and purple lines. You can see that. See how bad SGD is, right? You can see it even at the end of the animation. It's not even close to converging to our star. Whereas the rest of our examples like made it there a long time ago, right? So if we actually look at the order in which these guys get to the result, we can see that momentum, I think, gets there second to last, right? So the only thing it beats is SGD. And then Nesterov accelerated gradient makes it a little faster, right? So our purple one gets there a little faster than momentum. So we can see it's a slight optimization on top of our vanilla momentum. And then we can see these other methods, AdaGrad, AdaDelta, RMS prop, getting there really, really fast. And the big idea behind these three remaining things that we're not going to go into too much detail in the interest of time is that they use methodologies to dynamically update the learning rate. And generally speaking, what you want to do is you want to start off with a higher learning rate. And as you get closer and closer to your local minimum, you want to use smaller learning rates, right? Hopefully this makes sense because when we're first starting off, we don't want to have a very small learning rate because one, we want to traverse things quickly, get a feel for kind of the shape of our loss function at the beginning, see where potentially good local minimums lie. If we start at with a very small learning rate, we're just going to convert to some local minimum that's very close to where we started. And chances are that one's not going to be as good of a local minimum. It's not going to be as deep of a minimum as if we kind of look farther out amongst our loss function and then see, okay, are there actually like better local minimums here? And then once we kind of find an area that we're saying, oh, there's probably a decent local minimum around here, then we can start decreasing our learning rate to make sure we don't accidentally jump out of that little dip in our function, our little local minimum that we found. And then we can start kind of making more fine-tuned adjustments. So the idea is you start with a very large gradient or very large learning rate, and then you adaptively kind of decrease it over time. The manner in which you're decreasing it varies slightly based on AdaGrad, AdaDelta, and RMS prop, but they all use this general adaptive learning rate idea. And the last kind of state-of-the-art update method that we aren't going to go over, but we have a slide on it. Actually, it's not, I think it's the last slide if you guys really care. It's called Atom, and Atom kind of incorporates the best of all of these worlds. So it uses kind of momentum. It uses adaptive gradients as in adaptive learning rates, in order to, it kind of combines all these things in one, and then it gets a really really fast convergence compared to a lot of these other traditional methods. So hopefully that was a helpful visual for you guys to see, like, it does actually work. And hopefully it makes sense why it works. And then we're going to go on to our last topic, which I'll hand it back over to Varun, which is batch normalization.
Cool. So yeah, now this is going to be a little different from the other optimizations that we studied. Okay, honestly, not that different, but okay, let's look at it. So normalization, like it sounds, is mainly with respect to features. So you might have some features that are just like range between 0 and 1. You might have some features that range from 0 to 1,000. Now, obviously, it's not like if you have weights that have if you have features that have such different scales, uh, they're going to disproportionately affect the final output of your model, right? Maybe the feature that has entries in just the 0-1 interval is actually more important than the feature which has entries from 0 to 1,000. But just because of the scale, that feature is the one that's going to most impact your model. So that's obviously not ideal, and we want to correct for that. So also, once again, if you had some like honestly speaking, if you have a neural network that weights every feature and you train it for long enough, maybe you'll end up at the correct scaling. Maybe your neural network will automatically scale down the feature that ranges from 0 to 1,000 to 0 to 5 maybe. But if you provide some assistance to neural network right at the beginning before training even starts, you might reach an optimal solution a lot faster. So ideally, we want all our features to have a similar range. And it's empirically observed that if all your features have a similar range, then training happens a lot faster and you converge to a solution a lot faster as well. So this is a helpful visualization. So if you just have like if you just have two features, let's say X and Y, your X might have a very wide range, your Y range might be a little more limited. But once you normalize it, it becomes all central and symmetrical and nice looking. So how exactly do we implement this in practice? So note that it's normalization is not just for the input features, right? The primary selling point of a neural network is that it's automatically able to extract features from our input data. And so what that means is for any layer, its input features are the output of the previous layer, right? So the first layer's input is the actual data. The second layer's input is the output of the first layer, and so on. So you sort of want to know, we all normalize our data right at the beginning before training starts, but you also might want to normalize the inputs to every single layer, right? So that's why you do something like batch normalization. And you do something like this before you would use your activation function in neural networks. So once you multiply it, once you have your linear transformation, right? You multiply it by a set of weights, then you normalize your outputs, and then you apply your ReLU or sigmoid activation function or whatever.
Yeah, and in practice, it actually doesn't matter too much if you. I think a lot of current research suggests that it's actually better to normalize it after the activation, but it's not too important. So don't get too caught up on that. But the hopefully, okay, maybe there's some unfamiliar terminology on the screen right now. So like when we're saying logits, that just refers to the result you get when, let's say, through one layer of the network. So let's say we're trying to get the activations for our first layer. Okay. So we start with X, our inputs, and then we apply our weights to it, right? Our weight matrix. So we do WX plus B, right? We've all seen that hopefully when we feed forward. For every layer, we're doing WX plus B, and then we get to the next layer, next layer, next layer. So so the logits refer to the result you get from WX plus B. And then as we've learned, we always apply a nonlinearity and activation function to that WX plus B. So we've seen the sigmoid, right? We've seen ReLU. We've seen we've seen that that has a lot of effects of kind of providing nonlinearity to our model. and in and of itself, reducing the range of possible outputs. But we also want to perform this batch normalization to make sure that, like Varun's been saying for the past few minutes, like we want to start it so the mean of all of our of our activations is 0 and their variance is 1. There's you also like add additional hyperparameters that let the model kind of change those statistics a little, but you heavily suggest to the model that, hey, you should try to keep your activations between or with mean 0 and variance 1. Now, another reason this is very helpful is if we kind of we don't have any slides on it here, but if we think back to how we update the gradients or how we calculate the gradients using backpropagation, we remember that the gradients are a function of the activations themselves, right? So to find the gradient, you need to at some point you end up multiplying by the values of your activations. Now, if all your activations are very, very, very large, for example, then when you multiply when you're finding the gradients and you end up multiplying by your activations at some point, then your gradient's going to become a very, very large value. And then this has the same problem of choosing like a very large learning rate, right? Then you're not going to be able to converge to anything. And then conversely, if all of your weights end up becoming like close to 0, then when you multiply by if your activations are all very close to 0, then when you multiply by your activations and they're all very close to 0, then your gradient's going to be very close to 0. And then this has the same problem of choosing a very small learning rate, right? Then we're barely going to move anywhere. So if we keep our activations kind of with mean 0, variance 1, then this also ensures that our gradient isn't too big and it's also not too small. And then we can make appropriately sized updates based on our learning rate.
Yeah. So just formalizing the intuition that Paymon set out, what you sort of do is for every layer, you just subtract the mean and divide by the standard deviation. And then, so when you do this, zi hat is essentially going to have a 0 mean and unit variance. And after that, maybe 0 mean and unit variance is not necessarily the best for the inputs to the 20th layer or the 30th layer or so on. So what you do is, after you make it mean 0 and variance 1, you multiply it by two numbers, gamma, and you multiply by gamma and then add beta. So what essentially this does is that if you multiply, since zi hat originally had a mean of 0, zi tilde is going to have a new mean of beta, and it's going to have a new standard deviation of gamma. So what the cool thing is that with backpropagation, your neural network can essentially select the best value of gamma and beta for every layer. And so it's automatically choosing the best mean and variance for every single layer. It might turn out that the best gamma and beta are in fact like 1 and 0, in which case it's not really doing anything. That's perfectly possible as well. But in many cases, it might be more appropriate to have a different mean and variance. And it's cool that the neural network can just automatically choose those values for you. And we have a question that's asking, are gamma and beta hyperparameters? They're actually not hyperparameters, they are trainable parameters. So during your gradient descent stage, you can constantly keep updating these values. So gradient descent will automatically choose the best values for you. You might initialize gamma to 1 and beta to 0, but eventually it will just pick up the best weights depending on the best values depending on your network.
Yeah, and maybe one question that is in everyone's mind after this slide is, why did we do any of this then? If we start it with, we were saying earlier, it's really good to have mean 0, variance 1, because it keeps the kind of gradient values in check. And then now we're saying, oh, we'll let the network choose if it actually wants to abide by that or not. So then what's the point? If we just didn't do any of this, then naturally the network was going to choose its own kind of mean and variance anyway, right? So why is this useful? It's useful because it's So it's an additional constraint that provides a suggestion to the model about what kind of range of values it should keep its weights and biases within. Okay, so for example, right, we'll start it off. You usually initialize gamma to 1 and beta to 0, right? So then we're going to start off with what we said earlier, where we have very standardized statistics across every single layer, and that has the nice effect of keeping our gradient values in check. Now, like what Varun was saying, the network could say, okay, maybe I want the mean for this particular layer to be 2, right? And then it has the freedom to do that. But why this is a lot better than not having anything in the first place is it keeps the values in check somewhat, right? Because we initialize these values to be 1 and 0 at the beginning, it's very unlikely that the model is going to go off wildly somewhere else and be like, I want my mean to be 4,000 and my variance to be like 1,000,000 or something. It's not going to do that because that's never going to be empirically, that's never in the best interest of the model. But what ends up happening if you don't use this batch normalization is that sometimes just by randomly, when you initialize your weights, you're going to have your layers like have these very outlandish statistics of, oh, this layer is going to have a very large mean and variance. And that's not in the best interest of the model. So what we do is we say, okay, start at 1 and 0. If you want to change it a little bit, that's fine. But it at least it kind of gives the network an idea of, okay, I should be around these areas. Because we as machine learning engineers have empirically looked at this and been like, okay, it's better to have values close to this range because of these problems that I discussed. You don't want your gradients to explode to very large values, and you don't want them to be very small values either. So this first provides a little bit of flexibility to these two hyperparameters provide a little bit of flexibility to the model if it wants to deviate a little bit from the standard statistics, but not too much. And just to clarify, so these two hyperparameters exist for every single layer in the model. Okay, so these are not. It's not for one network. You're not going to have just one gamma and one beta. You're going to have 1 times the number of hidden layers, right, for your gamma, and 1 times the number of hidden layers for your beta, because these two learnable parameters exist for every single layer. So hopefully that's clear. And hopefully, just following up with the question in the chat. So hopefully we understand the difference between a hyperparameter and a learnable parameter, right? Hyperparameters are things that are static throughout the model, things that are not going to be changing, right? So like the initial value of our learning rate is a hyperparameter. I say initial value because with some of these adaptive gradient techniques, it'll adaptively change the learning rate, but the value that we start the learning rate with, for example, is still up to us. The number, there's a lot of different hyperparameters, right? The number of, I guess you could consider the number of hidden layers a hyperparameter in a sense. We have to choose that. The loss function you use, these are all things you have to choose on your own. Anything the network learns on its own through gradient descent, we call a learnable parameter. So because, like Varun said, we learn gamma and beta by performing backpropagation and gradient descent the same exact way that we do it for our weights, it's considered a learnable parameter. Yeah. Thanks for hanging in there, guys. We have like basically 0 slides left. We have like 1 slide left. So you can go ahead, Varun.
Yeah, we've covered all of this. And yeah, if you all want to go ahead and read more about batch normalization, there's definitely a lot of content online. Some hypothesis is that it's something to do with an internal covariant shift. I honestly don't know what that is, but feel free to look up more detailed analysis of why batch normalization works. Yeah, and I guess that's about it for our workshop. If you go to the Colab notebook that's linked, you can actually play around with a lot of the models that we discussed in the workshop today. And you can just play around with it. We're not going to be doing that during the workshop, but I can just show you what it looks like. You can essentially just run all the cells, read in the MNIST data, vary some regularization parameters, choose what percentage of cells you want to use in your dropout, whether you want to perform batch norm or not, what your initial learning rate should be, and so on. You can also choose what your optimizer should be. So this could just be momentum. It could be the accelerated gradient that we discussed, could be Adam. And finally, once you do all of it, you can train it. And once you train it, you can get some plots about what the training accuracy and the validation accuracy looks like. And you can just use this to get a feel for how you should go about choosing the best optimization framework for your machine learning model. Feel free to make a copy of this notebook and just, for example, play around with some of these parameters. So you could like maybe change the batch size, increase the number of epochs, or basically just play around and see if you can come up with a model that does really well.
And hopefully, sorry if I cut. Actually, go ahead. Go ahead.
Oh yeah, no, that's about it.
Okay, cool. So hopefully, what you'll observe if you take the time to look in this notebook is if you kind of set all the sliders for all these regularization terms that we've discussed throughout the workshop. If you set them all kind of to 0, if you kind of turn all of them off, hopefully you can see in the plot that you will likely get better. My guess is you'll likely get slightly better training accuracy, but you'll get a lot worse test accuracy. So if you play around with some of these sliders and you tune them to cool and good values, you'll eventually find that although it might not do better on the training set, it'll very likely do better on the test set. And that's, like we've discussed earlier in the workshop, that's kind of the whole point, is we care about the performance on the test set. And this is specifically with regards to these parameters on the screen right now, like regularization magnitude, dropout, batch normalization. So those three are the kind of big three for the regularization that we've talked about. And then we also have, just the learning rate, something we've all hopefully been familiar with in the past. You can look at the different optimizers. It's kind of hard for maybe you to visualize if one's converging faster just using this notebook. What you will empirically find is that Adam will usually do the best job because it uses momentum and it adapts the learning rate appropriately. If you are really interested in looking at the performance of the different optimizers, the link Justin sent a little higher up in the chat, if you guys scroll up a little bit to the link he sent, I just clicked on that during the workshop. I hadn't seen it before. It's really good. Like this, I'm just looking at this right now, and a lot of the things that me and Varun were talking about, and we didn't have great visuals to describe what we meant, is perfectly visualized in this link that Justin sent. So this is actually really amazing. I'm gonna bookmark this. So I would highly recommend looking at that. But yeah, thank you guys for coming out. There's one last slide on Adam. If you guys are interested, it just talks about the formula and for the update rule, and hopefully you'll see that it's kind of, some parts of it are similar to the momentum, because it literally is partially that. So yeah, hopefully you see some similarities there. And if you have more questions about it, please ask us on the Discord. Yeah, Justin just sent the feedback form in the chat for you guys. As always, we really appreciate your feedback, especially with Advanced++, since this is one of the more recent tracks that we've developed in, I think it's like a year or two old. So a lot of these slides are, as you can see, sometimes me and Varun wanted to explain something, and then we were like, wow, it would have been really nice if we had a slide for that. So next time, even just based on what we noticed when we were teaching, we'll definitely make some adjustments, and we'd of course really appreciate your guys' feedback as always, for anything that would make it more clear. Just off the top of my head, like, we'll definitely try to put some more visuals. A lot of those things in the links we sent, we'll try to incorporate those into the slides, but anything else that you guys have to tell us, we'd really appreciate it. So yeah, Justin or Varun, is there anything else?
Yeah, no, that's about it. I hope everyone has a feel for what optimization techniques are used in ML, and it's like a platform for all of you to go out there and learn about more of them, because there's a lot that we couldn't cover in this one workshop, but hopefully this was a good starting point. And yeah, like Paymon mentioned, please fill out the feedback form. It helps us improve our workshops in the future.
And just a note, if you guys are working on your own personal projects or looking into more things about optimization or anything else about machine learning, feel free to stop by our office hours. They're held in Discord at 9 p.m. on Thursdays. So if you have any questions or just want to talk things over, feel free to join through there.
Yep. Okay. I think we can stop the recording.
Yeah.